Imagine I told you I built a bridge based on some metaphors, but not a real physical model that predicts its strength. Would you trust that bridge? Of course not. You'd demand exact data, load limits, fatigue tolerances, safety margins. Yet in fitness, we lean on a model that lacks any of this precision. It's accepted largely because it's simple and has been around forever. Today, we're dissecting one of the most persistent but deeply flawed models in the world of fitness: supercompensation. Hi, I'm Dennis, a certified fitness coach and German engineer. I apply numbers, logic, and systems thinking to my training and help others to do the same. Why to delete supercompensation out of the dictionary? As an engineer, I love models, whether it's thermodynamics, signal processing, or structural mechanics. Models allow us to grasp complex systems and make informed, testable predictions. When they're well constructed, they're not just useful, they're powerful. But when models are built on flawed assumptions or vague inputs, they do the opposite, they mislead. At first glance, it seems elegant. You train, your performance simply drops, you recover, and then you rebound stronger. The idea is that your body doesn't just return to the baseline, it overcorrects. This overshoot is what's meant by supercompensation. It's been repeated in textbooks, certification programs, and YouTube videos for decades. The graph always looks the same: a neat dip followed by a peak, then another dip if you train again. Rinse and repeat. But let's slow down and ask first the critical question. Does this model actually reflect on how the body adapts? Does the term supercompensation even make sense? Let's start with the language. Compensation means returning to balance. Super implies going beyond that, but using both terms together is like saying ultra-equal balance or hyper-recovery equilibrium. It sounds scientific, but it's just not helpful. It's terminology that confuses more than it clarifies. Now onto the graph. The famous curve is often presented without any defined units. The y-axis says performance or system status, the x-axis says time. But what exactly are we measuring? Is it strength, tonic output, muscle protein synthesis, satellite cell activity, hormonal levels, substrate availability, or neuromuscular coordination? Nobody tells you. The ambiguity makes the graph more metaphor than model. And in engineering, metaphors don't fly. Let's dig deeper into its flaws. The supercompensation model assumes a simple cycle: stress, decline, rebound, improve. But that doesn't reflect how many systems actually work. Take bones for instance. Bones don't adapt to become as strong as possible. They adapt to become just strong enough. That's the principle of structural efficiency. The goal isn't more, but enough. So the whole idea that biological systems always overreact to stress is wrong. Moreover, muscle adaptation doesn't rely on a single recovery curve. It's driven by a complex interaction of signaling molecules. These are multi-layered processes operating on different timescales and feedback loops, none of which can be reduced to a tidy curve. Even this idea that every workout causes a dip in performance is questionable. In trained athletes, a typical session doesn't always produce a measurable drop. In fact, some experience a short-term boost thanks to neurological priming, improved blood flow. So if there's no reliable dip, what's the curve even predicting? And even when there's a dip, the timing of recovery is far from universal. The classical model tells us to hit the next session during a so-called supercompensation window, usually said to be between 48 or 72 hours. But what happens in that window depends on dozens of variables: your training volume, intensity, sleep, nutrition, stress, training age, and even which muscle group you trained. For some, protein synthesis might peak at 24 hours. For others, it might barely register. There's no single curve. There's never was. So using a static timing model for something so dynamic is like trying to schedule rocket launches using weather forecasts from last month. And that brings us back to engineering. When we model a system, whether it's an engine, a signal amplifier, or a high-rise building, we ask two questions: what variables define the system and how they interact over time? If we don't have clear inputs and measurable outputs, we don't pretend the model works. But fitness often does exactly that. We train based on a vague curve and hope for a magic peak. That's not training, that's gambling. Real systems thinking is different. Let's look at a better approach: adaptive recovery and load management. Instead of assuming that body rebounds after every stressor, we track trends, fatigue levels, performance, readiness, HRV bar, speed, soreness, nutrition, and sleep. These inputs give us real-time feedback to inform our next decision. It's less elegant than a curve, but it's real. Likewise, hypertrophy isn't a bounce, it's an accumulation. Adaptation builds slowly over time with sufficient mechanical tension, metabolic stress, and progressive overload. The body doesn't supercompensate, it adapts. It integrates stimuli over time and changes based on need, not on a timer. Thinking otherwise is like assuming your phone battery charges faster if you use it first. It doesn't work that way. So how did supercompensation even catch on? It started in endurance sports. When runners deplete glycogen stores and then carb load, they can temporarily exceed baseline glycogen levels. That's real and measurable, but glycogen is a fuel reservoir. Muscle is a structure. One is short-term chemistry, the other long-term tissue remodeling. Applying the same model to both is a category error, and yet it persists, probably because it's easy to teach. Coaches love tidy frameworks, but science isn't tidy. Biology is messy, and if you want to train effectively, we need models that match that complexity. Finally, let's talk logic. As we said earlier, supercompensation is a contradiction. You can't overbalance something. Either the system returns to baseline or it adapts to a new state. If it adapts, call it growth. If it returns to baseline, that's just recovery. But mixing the two, that's just bad labeling. In engineering, we never accept such a term. We don't say super return to equilibrium or ultra homeostasis. We define what's happening with precision and we don't stack buzzwords to sound impressive. Fitness should do the same. So next time someone throws the classic supercompensation graph at you, ask them what exactly is being measured, what units, what timing, and what mechanism drives the change. If they can't answer clearly, it's time to question the model. Don't let outdated ideas shape your training. Think in systems, look for data, adapt with purpose. Because if you want to train like an athlete and think like an engineer, you can't afford to rely on fairy tales. You need models that work, not just ones that look good in a slide deck. If you want to learn when science may not be helpful, check out this video right here. Thank you for watching, and until next time, this was Denis. Bye.